To the fourth lecture of this series on abelian varieties over finite fields. So today we are going to discuss the Veil conjectures. And before we do this, I'm going to again supplement some of the things we saw about endomorphism ring of abelian varieties. So okay, so the thing that I want to do is to start by giving you additional properties on the endomorphism ring of abelian varieties. So namely, we're going to start with the classification by those, the classification of that endomorphism ring by Albert. Okay, so we let A be an abelian variety over a finite field. And we want it to be case simple. Of dimension, case simple abelian variety. So we want it to be dimension G over our finite field. Then we let D be the endomorphism ring, or the endomorphism algebra to be more specific, of A over our base field. Then one of the results we saw last time, Wedderburn. So Wedderburn says that D is a division algebra. So basically what we are going to do now is to give a refined description of this abelian variety, this division algebra. So for this, we are going to let F be the center of D. Now, what we are going to let X to X dagger be the Rosati involution. So this would be the Rosati involution. On our abelian variety A. And what we know about this is that this is a positive involution. So the main takeaway from this is that if we consider the fixed field of that involution, so in that case, I'm going to call this field F dagger, and it would be all the elements that are in the division algebra, such that under the Rosati involution, they are equal to themselves. So this field, the consequence of the fact that the Rosati involution is a positive, this is a totally real number field. So is a totally real number field. So what does this mean? Every embedding so if you take any embedding of, which I'm going to call sigma from F dagger into the complex, then this embedding will factor through the real number. So that's what it means for this field to be a totally real number field. And of course, we have that F dagger is contained in F. Okay. So now, what we are going to do. So now we are going to let E be the degree of F over Q. And then we are going to let E dagger be the degree of F dagger over Q. And we are going to let D be a square root of the dimension of D over F. Right, so if you have a division algebra, the dimension, it would have square dimension over its center. Okay, so now these are the notation that we need in order to state the Albert classification theorem. So Albert classification. So we keep the notation above. We're keeping the notations above. The algebra D is isomorphic to one of the following types. To one of the following type. And the thing here, there are 4 types. So type 1. In that case, your division algebra is simply equal to its center, which is equal to F dagger. So, and in that case, the Rosati involution would just be the identity. And so in that case, the degree of F will divide G. So that's the first case. Type 2. So in that case, we have that F is equal to F dagger, and that D is a totally indefinite quaternion algebra over its center, which is F. What that means is that, so for all embedding sigma, so for all embedding sigma of F into R, remember we saw that those embedding would be totally real. Then if you take the tensor product of D with R via that embedding, you get an algebra which is isomorphic to the 2x2 matrices with real coefficient. So when we are in this case, then we have that 2E will divide G. So that's type 2. Type 3. So now type 3. So in type 3, F is equal to F dagger, and D is a totally definite quaternion algebra. So that's essentially the opposite of what we saw in type 2. So what this means is that for all embedding sigma of F into R, if you take the tensor product of D over that embedding over R, you get the Hamilton quaternion algebra. The Hamilton quaternion algebra. Okay, so in that case, we will have that the square of E divide G. So that's the third case, and now we go to the fourth case. So in the fourth case, F is a CM. It's a CM extension of F dagger. So what that means is that it is a totally imaginary quadratic extension of F dagger. And D is a division algebra whose center is F. And in that case, we have the following. So in that case, you would have that E dagger times D squared divide G if the characteristic of the base field K is equal to 0. Or you would have that E dagger times D divide G if the characteristic of the base field is positive. So that's quite a lengthy statement, and this is known as the Albert classification. Okay, so that's the Albert classification, and whenever we need it, we'll just consult it. So now we can move to Abelian varieties or zeta function of Abelian variety. So that would be zeta function of Abelian variety. Of course, when I say this, I always mean over a finite field. Right, so the first theorem we are going to need is the following theorem. So A is an Abelian variety over FQ, a finite field of dimensioned dimension of F is equal G. And here FQ, Q is equal P to the N. So P is equal to the characteristic. And N is an integer. So then the theorem says that you have the following. Every complex root of the characteristic polynomial so every root alpha or in C of the characteristic polynomial Fa of pi a has the following absolute value, has absolute value alpha equal square root, absolute value of alpha is equal square root of q. So that's the first part of the statement. The second part of the statement says that if alpha in C is complex, then so is alpha bar, which is equal to alpha over q. And not only that, the two root would appear with the same multiplicity. So they will appear with the same multiplicity. Okay. And now finally, if alpha is equal square root of q or minus square root of q is a root of Fa, then the multiplicity will be, then it would have even multiplicity. Okay. So because we are not going to prove that many theorems today, let's at least give the proof of this one just to warm up. Okay, so proof. So the proof, so So that's the first part. This starts with a reduction argument, so reduced to the case of a simple Abelian variety. So once you've done that reduction, then everything kind of becomes simple. But we know that if we start with any abelian variety, if it admits a decomposition into simple abelian varieties. So assume that A is isogenous over FQ to A prime, and that we can write A prime as A1 cross cross AS, where each of those AI is simple. Okay. Right, so we call this isogeny H. Then because this is an isogeny, it will induce an isomorphism. So the isogeny H induces an isomorphism of Tate module. Right, so that isomorphism, we call it, so the notation we use is VL of H, and we go from VL of A to VL of A prime, which is now a direct sum. So it would be VL of A1 VL of AS, right? But one of the nicest properties of the Frobenius is that it commutes with almost everything. So we have that if we compose H with the Frobenius map on A, this would be the same as composing the Frobenius on A prime with H, right? And if what that means is that if I look at the automorphism, so the automorphism, that I have, VL of H, VL of H composed with VL of H composed with VL of, sorry, this one is composed with VL of pi, composed with VL of H inverse. This will be equal to VL of pi A prime. Right. So if I conjugate the Frobenius automorphism on the Tate module of A by the isomorphism induced by the isogeny H, it would recover the Frobenius automorphism on the Tate module of A prime. So that's what it means. But clearly, in that case, we see that the V, if we take the Frobenius the Frobenius automorphism on A prime would simply be given by as basically a direct sum. So the Frobenius automorphism, which goes from VL of A prime to VL of A prime, will send, if I take x1 xs, it will simply send this to VL of pi a1 x1 up to VL of pi as applied to xs. So in other words, the Frobenius endomorphism on the third module is simply obtained by taking the direct sum of the Frobenius endomorphism on the different factors. And what that means is so this implies that if I take the characteristic polynomial of Frobenius for A, it would simply be the characteristic Frobenius of A1 times the characteristic Frobenius on A2 up to the one on AS. So that this means that it's enough for us to prove the statement in I for simple abelian varieties. So enough to consider a simple abelian variety. Okay. And so now what we do, so let lambda be a polarization in A, and then we're going to let dagger be the Rosati involution induced by that polarization. Okay. Then what we are going to start by showing that. So we first show that if we take pi A composed with pi A dagger, it's simply the multiplication by Q on A. So that's what we want to show. But if you look at pi A composed with pi A dagger, then by definition of the Rosati involution, this would be pi A composed with lambda inverse, composed with the dual of pi A, composed with lambda. But the key thing here is that as we saw, the Frobenius automorphisms commute pretty much with everything. So this would be pi A composed with yes. So the fact that these commute mean that this would be equal to lambda inverse pi A composed with pi A dual with lambda, right? So it is enough it is enough to show that if I take pi a composed with pi a dual, I get the multiplication by q on the dual. If we can prove this, then clearly the multiplication will commute with the polarization, and then lambda times lambda inverse the identity. But by definition, if you look at, if you remember when we wrote the definition of the Frobenius endomorphism, in this case, it's just the Frobenius endomorphism of A over the base field FQ, and then we compose it with itself n time, where n is the degree of the base field F. Now we are going to see in the next section the Verschiebung. So by the properties of the Verschiebung map, the properties of the Verschiebung map. So I'm going to write C next section, C next lecture to be more specific. We have the following. So these are very easy properties of the Verschiebung that we are going to see. So we will have that if we take the dual of the Frobenius endomorphism, this is simply the Verschiebung endomorphism and the dual of A. And not only that, we are going to see that if you compose the Verschiebung with its Frobenius with Verschiebung, you recover essentially P. So we're going to see that if you take this, compose with this, so this would be the same as taking the Frobenius of A dual over FQ to the nth power composed with the Verschiebung on A dual over FQ to the nth power. And these, when you compose them, you would see that they are simply P to the n on A dual, which is Q on A dual, because the degree of the field is n. And so we have that when we compose pi A with pi A dagger, then we recover multiplication by Q on A. Okay, now we are going to combine that with the fact that A is simple. Right. A is simple. This means that if we take the subring generated by the Frobenius in the ring, this would be a number field. I mean, this has to be a field. It's generated by one element over Q, so it has to be a field. And therefore, since we saw that the characteristic polynomial of Frobenius as integer coefficient, this will be a number. It will be a number field. Now, furthermore, we saw that Fa is a power of the minimal polynomial. That's one of the propositions we saw in the previous section. Minimal P of of pi a. Okay. So that means that the complex roots, if I look the complex root of, so look at the complex root of the polynomial g, and hence fa, there would simply be the conjugate of pi, because we already know that pi is the root of the polynomial. And because it's an irreducible polynomial, given that a is simple, any other root would have to be a conjugate of pi. So the complex root of g, and hence fa, are of the form iota pi a, where iota is just an embedding of the field generated by pi a into C. And of course, that gives the first part of our statement. So the relation, right? So remember, we have that pi a times pi a dagger is equal to q on a. So of course, that means that the root would be stable under the So this would mean that if I'm looking at this field, it will be stable under the Rosati involution. So it would be stable under the involution dagger. And remember that this is a positive involution. And being a positive involution, it means that we will have two possibilities. The first one being that we are in the totally real case. In the totally real case, this means that yeah, so this is a bit redundant, so this is totally real. And dagger is just identity. So it's just the identity map. Okay. And the second case would be the CM case. So in that case, so Q pi is the CM. And if this is a CM field, this would mean that for every embedding iota which goes from Q of pi a into C, if I take the embedding of x and the one of x dagger, they will be the same, and this would be true for all x and Q of pi a. Right, so that's the CM case. And then we see that in either case, this would mean that if you have a complex root, it will have the right absolute value. So So in either case, we see that this identity that we wrote a bit earlier, pi a times pi a dagger equal q, this would imply that if alpha in T is a root of FA, then the absolute value would simply be the square root of Q. So that gives the first part of our statement. And now we move to the second part. Okay. The second part. So the first two assertions, I'll leave, they are really not that hard to prove, the first two assertions. To prove, so this will be an exercise for you guys. So we move to the second one. So assume that alpha equals square root of q, or alpha equal minus square root of q is a root of fa, right? So that tells you that then this would mean that the field, this field cannot be a CM field. Right, because if this were a CM field, then all the root of the polynomial would be complex. Right, so this means that the field is totally. So this means that Q pi A must be totally real. Right, we know that there are only two possibilities. Right, and we know that in that case, we know that the only possible root right, so the only possible root are because we have alpha equal alpha bar equal q, so this will be the only possible root. In that case, the only possible root, sorry, the sentence is not very well written. Yeah, so in that case, the only possible root are alpha equal plus or minus square root of q, because of this relation that we saw earlier. The relation alpha bar is equal to q. Right. Now we want to see that if let's say square root has multiplicity, let's say square root has multiplicity m. Right. So multiplicity m. So the key thing here, you can relate these multiplicities to the root of the polynomial, right? Then, because the degree of the polynomial is 2g, this would have a multiplicity of 2g minus m. Right. And now, if we look at the value of our polynomial at 0, then this would simply be minus 1 to the m times q to the g. But we also know that this would be equal to the degree of pi to the a, or minus pi to the a. And the degree of an endomorphism is always positive, and in this case it's q to the g. Right. So this would imply that minus 1 to the m q to the g is equal to q to the g. And this is only possible if m is even. And so this complete the proof of this theorem. So in the end, it's quite a lengthy proof, but we are done. So at least we've done one proof today, so we can rest for the rest of the lecture. Okay, so now we're going to define the zeta function of a scheme. So let X be a scheme of finite type over a finite field FQ. Then for any integer n positive, we are going to let capital NN be the number of points on the field FQ to the n. So the number of FQ to the n rational point. Okay. Then using this, we can define the zeta function of our scheme. So the zeta function of X is defined as follows. So it's an infinite sum. So denote this, how we were going to denote this. So it's exponential, and then n going from 1 to infinity of n divided by n times t to the n. So you can see this as some kind of formal power series in T. And the Veil conjecture, which are in fact theorem now, says that this has rather striking properties, right? And that's the content of the following theorem. So we keep the notation above, so let A be an Abelian variety over FQ over FQ. And then we are going to write the characteristic polynomial. So this is a product, I going from 1 to 2g. t minus alpha I. So basically, all these are the roots of the polynomial. And writing the polynomial this way means that we are counting the root with multiplicity. Okay. And then, so the first part of the statement tells us that you can use this to recover the number of FQN rational points. Right. So, if I want the number of points that are defined in FQ to the n, all I have to do is compute the following product. So I'm going from 1 to 2g, and then I take 1 minus alpha I to the n. Right. So that's the first part of the statement. And the second part says the following. So the zeta function of is actually a ratio of polynomial. So is a rational function. It's given by, so we'd have z of a t. So this would be a product that can be expressed as follows. So we've said this is P1, P3, P2G plus 1. So that would be the product on the numerator, and the denominator would be P0, P2, P2G. And where each, so if I call this pk of x or of t, has integer coefficient, right? So for each k going from 0 to 2g, the polynomial pk would have integer coefficient and is given explicitly in terms of the alpha I as follows. So if you want pk of t, all you have to do is you consider all the subsequences of the following form, all the subsequence with k element between 1 and 2g, and then you take 1 minus the root in index, or the root of the polynomial index by that sequence. So 1 minus alpha I1 dot 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 I alpha IK times t. Okay. So that's the second part of the statement. And the third part says that we have a functional equation. So the functional equation being that if I take z of a 1 over q to the g times t, I get that this is Z of AT. Okay. So we are not going to prove the theorem, but there are enough detail in the lecture note. The proof really are not that hard. They just use basic linear properties, basic properties of linear algebra, combined with some functoriality related to the Frobenius endomorphism.